Hello, you are welcome to our tutorial. This is our third tutorial, but this tutorial isn't control system, it's digital electronics. Digital electronics. Okay, digital electronics. What are we going to learn today? We are going to learn about partial decoding. Partial decoding. Partial decoding. Okay, partial decoding. When you hear partial decoding, you have to know flip-flops. Okay, you have types of flip-flops. You have SR flip-flops. You have JK flip-flops. You have flip-flops. You get it. But today we are going with partial decoding. Partial decoding. What does it basically means? It means decoding numbers or series of sequence. Okay, so decoding series of sequence. That's partial decoding. So they can give you a question of decoding 11. So how do you decode 11? Because we know that our flip-flops is having 1, 2, 4, 8, 16, 32, 64, 54 bits. So how do you decode 11 odd numbers like 11, 12? I'm going to show you through the process step by step. Okay, so flip-flops, that brings the topics to flip-flops. That brings the name flip-flop. Flip-flops are basically using the application of flip-flops are using counting. You are using frequency divider. Okay, for flip-flop, that's positive flip-flops are used for frequency dividers, and negative flip-flops are using counting. Okay, so let's use negative flip-flops. Okay, so flip-flops, basically the first question, the best way to solve a question or understand a question is to solve it or solve problems with that. So let's solve the first problem. The first problem is getting our 11 or designing our circuits of 11 to decode 11. Okay, we are going to decode 11. So basically I told you that we are going to use flip-flops. Flip-flop is a bit. One flip-flop is 1 bit. Okay, so what we have to do now, you have to know our flip-flop diagram, how it looks like, and a whole lot of things. So right now, how are you going to solve this? So how do we determine the number of flip-flops that can decode 11? So basically, in number basis, we use this system. 2 raised to the power 0 is what? 1. 1 flip-flop, 0 flip-flop can decode 11. Never. 2 raised to the power 1 is what? 1 flip-flop. The power which the flip-flop, the number of flip-flops. 1 flip-flop is what? 2. So 2 bits. 1 flip-flop is giving us 2 bits here. Okay? 2 bits. Can it decode 11? No. 2 raised to the power 3 is giving us what? 8. 2 raised to the power 2, sorry, is giving us 4. 4 can't decode 11. Okay? 2 raised to the power 3 is giving us 8. 8 can decode it. 2 raised to the power 4 is what? 16. 16 can. So 11 is in the range of 16. Okay? The range of 16. That means that we're going to use 4 flip-flops. You see, that's how to identify the number of flip-flops we are going to use. Okay? So the idea is we are using 4 flip-flops. Keep in mind how we get the number of flip-flops used. Okay, so basically we have to draw our truth table. Okay, our truth table to be able to decode, because 16 and 11 is less than 16. So how do we get the exact 11? So I to know 11, 12, 13, 14, 15, 16. So that's where we are going to decode. So decoding basically means sending some output to a NAND gate. Okay, a NAND gate. So basically, let's draw our truth table. We are going to number this truth table very fast. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So basically, this is our number. We are going to use our truth table. So it's the same truth table we know in NAND gate, AND gate, OR gate, and all the logic gates. So you name it Q0, I have 0, So this is the numbers. Let's differentiate the numbers from the coding bits and let's see what we are doing. We have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, so next one we have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Okay, the third one, this is Q2, Q3, Q1, Q0, Q1, Q2. Okay, Q2 we having 2 raised to the power 2 is what? 4. Okay, so you're having 4 zeros, 4 ones. So let's go 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay, so the next one is what? 3. Q3. Q2 to the power 3 is having what? 6. 2 to the power 8 is 2 to the power 3 is 8. So you are going to have 8, 0, 0, 0, 0, and 8, 1, 1, 1, 1. Okay. Are we on the right path? Yeah. You're having 8, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. This 8 zeros and 1, 1, 1, 1, 1, 1, 1, 1. That's 8 ones. Okay. So we are going to decode. How do we decode now? We are decoding 11. So what decoding 11 basically means we are going to have a series of sequence from 0 to what? 10. It wouldn't read 11. Okay? So 11 code will not read 10. Will not read 11. It will read up to 10. So our truth table, where is our 11? We identify our 11. Let's name it. How do we name it? We name only the ones. Okay? We name only the ones. So that Q3 is a 1. Q1 is a 1. And Q0 is a 1. Q0 is a 1. Okay? Q3, Q1, and Q0. Okay? Let's go. So we are going to draw with the help of this. With the help of Q3, Q1, and Q0. We are going to draw our flip-flops. We are going to draw the circuit for our flip-flop. That's what is important, not the truth table. The truth table is going to help us get our flip-flop circuit. Okay? Good. So let's claim here. We know the number of flip-flops to draw, so we are not having a problem. We know our outputs and our NAND gates, so we are not having a problem again. Let's draw our flip-flop. How does a flip-flop look like? Oh, this marker. A flip-flop, let's draw the box first and arrange it in order. Right? This side, this side. Okay, this side. Good. It's a JK flip-flop, so we name it a JK flip-flop. And it's a negative flip-flop, so we have a knot here. We have our, it's a high, it's a toggle state. So we have it like this. When J and K is high, it's called a toggle state. Okay, and you have a Q here, Q0, 0, 0. And you name it flip-flop 0. Okay. This will move to will feed another flip-flop. The same design, but we name it J1. It's a not C. We name it K1. Having Q1. Move to another state. The same. You have J2. There is a knot, okay. C, okay, 2. You having Q2. Move to the last third one. Because we need 4. 2 is the power 4. We need 4 flip-flops to get 16. After the 16, we decode to get 4. 11. We decode to get 11. Sorry. Have J3, K3, not have our C, and the Q3. So flip flop 1, flip flop 2, flip flop 3. Okay, 1, 2, 3. Okay, that's good. So we have our NAND gate to do our toggle to do. What did this NAND gate do? Basically, the NAND gate will detect the flip flop, will detect the code, and automatically change it to zeros. So this, it acts as a changer. So let's say a changer. So when it sends the input that you send, it sends the input you give it. It just change and start the whole functions as 0000. You start from counting 0000. Okay. So what does this a NAND gate? What does it do? When it sends the input, it automatically change the counting system and start it from 0. Okay. So we need so we're having 3 inputs. So this will be a NAND gate with a 3 inputs. 3 inputs. My marker is not working. A 3 input NAND gate. Okay. 3 input NAND gate. The first one is you can kill 3. So kill 3 is here. Move here. That's our kill 3. You have kill 1. Our kill 1. Where's our kill 1? Move here. That's our kill 1. Then what's kill 3? Kill 0. Kill 0 is here. Move here. So it's a 3, kill 0. Okay. So this is a 3 input. Input NAND gate. NAND gate. Okay. 3 input NAND gate. We are not done. So the high you have to, because it's a toggle state, all the highs will be connected to the top. All the highs. You need all the highs alone. Okay. Connect all the highs to each other. And the output of this will be connected to the clock. That's the clear. Okay, sorry, the clear. So connected to the clear like this. Hope you are getting the story. It will be connected to the clear like this. Deep in the side. We are done for the day. That's for 11 to decode 11. Okay. Our next video, I'll decode 34 and 68. Watch out.